Okay, so I'm not super used to doing things on Zoom, so hopefully I'm doing everything right. Um, you can see the screen share, correct? Okay, awesome. Okay, so I'm covering geometric series, which is a very specific type of um, sequence, basically. Um, so a geometric series is the sum of the terms of an infinite geometric sequence. So we can have finite geometric sequences where they end, and then we can have infinite where it doesn't end. And a geometric series is what we call for the type that doesn't end. So it doesn't just mean it's, a series basically is a sum of a sequence, but we give the name geometric series specifically to the infinite version. So we've got basically you're just adding your terms together, A1 plus A2 plus A3, and you go on forever. Or if we put it into what a geometric sequence looks like, where you have a ratio that you're multiplying by, and each term gets multiplied by that ratio again, it really looks like A1 plus A1R plus A1R squared, and then A1R cubed, because each term is the previous term times R. So you just keep increasing your exponents on R. And so that allows us to write this in summation notation. And we use S to represent the sum. So we've got the sum from starting at 0 to infinity of A1R to the I. Or if you start counting at 1 instead of 0, you have to modify the formula slightly so that it's I minus 1 in the exponent. They are essentially equivalent formulas. It just depends on where you're starting your counting. Most of the time we start counting with 0, but sometimes you'll also count by 1. It kind of, it depends on where you're naming things. And so just you want to make sure you're using the correct notation, but the two are equivalent. So obviously this is infinite, so you're not going to be able to add this by hand. And yes, R is the ratio between terms. So I can write that here. R is the ratio between terms. That's correct. So infinite series, we're not going to we can't actually add it because it goes on forever. But we can take the formula for a finite geometric sequence where you're adding them up for the sum. And then we're going to do what's called the limit. And this is actually, we're going to talk about this in week 8, but you're kind of getting a preview. So for a finite geometric sequence, if you add up all of the terms, you get a formula, which is A1, and then that's times 1 minus R to the N over 1 minus R. So for an infinite series, or for a geometric series here, you're going on to infinity. So your N, which is the number of terms, just keeps getting bigger and bigger. We can't really plug in infinity. We don't, that's not a thing that you do. But if you think about what R is, so R is a ratio, and for the most part, the value for R, whether it's positive or negative, it's usually positive, is usually less than 1. So like, let's say you have an R of 0.25. So the higher the exponents, the smaller the number gets. So if I take 0.25 to the 5th power, and just grab that on my calculator, that's 0.0009766563. And then if I do it to the 10th, it's even smaller, 0.00000954. So it's smaller. So the higher N gets, the smaller r to the n gets. And so presumably, as you get towards infinity, that value r to the n is going to get to 0. It's going to approach 0. We can't ever reach 0 because this is infinite, but it will get as close to 0 as possible. And so as far as we're concerned, we're going to basically say, okay, it becomes 0. Because you get big enough, it's going to be so small that it's going to round to 0. So when you substitute r to the n with 0 in the formula, it just becomes 1 over 1 minus r. And then that gives us our formula for a geometric series, which is for infinite terms, as a1 over 1 minus r. So it's very, very similar to the formula for a finite, the sum of a finite geometric sequence. It's just the top 1 minus r to the n basically disappears because of what happens when n gets really big, that r to the n gets small. So are there kind of questions on how we get this formula from our finite geometric sequence formula? Okie dokie. So the nice thing about this formula is that it's really easy to use. So let's just go through several examples. So I've got examples that are in summation notation. We'll do examples that are actually written out with the sum. And then we've got some word problem examples as well. And I will give you a heads up that the very last problem on the application assignment is an infinite geometric series. So you're going to have to use this formula when you answer that problem. So we've got geometric series here, and we're going to find the sum. So I'm going to just write down the formula again for the sum. S is equal to a1 over 1 minus r. Make that 1 a little, there we go. So if it's in the sum, the summation notation was basically I equals 0 to infinity of a1r to the I. So these are using n instead, but that's completely fine. It's still in the same form. So we're able to identify what a1 is and what r is from the summation notation. And then all we need to do is plug it in the formula. So it's pretty nice. So for the one on the left, a1 is equal to 2. And then 3/4 is equal to r, because that's what's being raised to the exponent. So r is equal to 3/4. So all we need to do is plug it into our formula. We have s equals a1, which is 2, over 1 minus r, which is 3/4. So when you simplify, that will give you 2 over 1/4, and then 2 divided by 1/4 comes out to 8. So the sum of this geometric series is 8. And if you were to start adding up term by term by term, and you would find that the sum is getting closer and closer and closer to 8. And if it goes on forever, it's basically approaching 8, and it won't get bigger than that. Now the example on the right, again, we have a1 equal to 2. And in this case, r is a negative. It's negative 2/3. And so when we put this in the formula, we get 2 over 1 minus negative 2/3. So we're actually going to be adding 2/3 in the denominator. And so 1 is 3/3. So 3 plus 2, that's going to give us 5/3. So we're going to get 2 over 5/3. And we're dividing by a fraction, which is the same as multiplying by the reciprocal. So the one on the left I could do in my head, that was simple enough, but I like to show a little bit more work if it's a more complicated fraction. And so we get 2 times 3, which is 6. So we're going to get 6 over 5 as the result of the sum. Now, just as a side note here, this formula for the sum is that absolute value of R is less than 1. You're not going to be ever asked to find the sum of the geometric series where R is greater than 1, the absolute value of R greater than 1, because there is no sum. Because if you have your R greater than 1, as it goes towards infinity, it doesn't get towards 0. It goes on, it just keeps getting bigger and bigger and bigger. So there is no one number for the sum if your value for R is greater than 1. So you're only going to see it if it is less than 1. You can have a negative, like we have negative 2/3, but that absolute value has to be less than 1 in order for this formula to work. And you're not going to be asked to do anything other than that because it's just not going to make sense. Are there any questions on these two examples? Okay. So one on the left, another one where we're going to use the formula. It's in summation notation. The one on the right, it's not in summation notation, so we have to do a little more work there. But for the one on the left, let's have you guys do this one as well. So I'll write down the formula again. The sum is A1 over 1 minus R. So go ahead, identify what A1 is, identify what R is, and then plug it into the formula and let me know what you get. And I'm going to do it on the screen as well, but let's have you guys also do it on your paper so that way you can practice, doing this and doing it on your own. All right, so we've got the answer of 5, which is correct. So A1 is 4, R is 0.2. So when you plug it into the formula, you have 4 over 1 minus 0.2. That will give you 4 over 0.8, and then that comes out to 5. If you want, you can convert the 0.8 to a fraction, and then, if that's actually how I did it in my head. I knew that 0.8 was 4/5. So I knew that the 4 on top and the 4 on the bottom from the 4/5 would cancel, and then that 5, the denominator would become on top because you're multiplying by the reciprocal. So that's how I got 5 in my head mentally. But yeah, using your calculator is totally fine. And with a lot of these, you're going to want to have your calculator handy. It's just going to make things a lot easier. Okay, so let's look at the one on the right. So this is not in summation notation. So you have a choice. You can put it in summation notation, or you just have to identify A1 and R and then plug it into the formula. So I wouldn't bother putting it in summation notation unless, you were showing your work for something. Let's do it for good measure. We'll do it. We'll just practice. We'll put it in summation notation as well, just so you can see what this means. But the first thing you have to do is identify A1. So that's going to be your first term. So that 9 is A1. So that's easy enough to find. R is the ratio between two terms. So it'd be like A2 divided by A1. And then you should also double check to make sure that this is a geometric series. So you could also do like A3 divided by A2 just to make sure that you get the same value for R. Because if you get a different value for R, then it's not actually a geometric series. So to find R, we're going to take A2 and divide it by A1. So the second term is 6 and the first term is 9. So when you reduce that, you can divide by 3, you get 2/3. And if you just want to verify, you can take A3 divided by A2. That's 4/6. You divide both sides by, or the top and the bottom by 2, and you also get 2/3. So R is equal to 2/3. So I could write this as the sum of I equals 0 to infinity of A1, which is 9, times 2/3 to the I. Or you can use N, you can use whatever letter that you want. And you could go straight to our formula for S from here. So we can put in the formula. So A1 is 9. And then we have 1 minus R. So that's 1 minus 2/3. So that's 9/1/3, which will give you 27. So that last problem on the application assignment where I said that it is an infinite geometric series, I would actually recommend that you either write out the pattern of the series, like how this problem starts out 9 plus 6 plus 4 plus ... Either write that out or put it in summation notation. You don't need to do both, but do one or the other to show what the series looks like, because you're not given the series in that question. You're told kind of how to create it, but you're not just like given the formula or whatever. So either write out the pattern or put it in summation notation, and then from there you can find the sum. Are there questions on this example I just did? I need a thumbs up. There is in Zoom somewhere. There are reactions. I have it under more, but there is actually a thumbs up reaction. And I think it puts it on your face or on your off camera, basically. But I think that's where it puts it. I'm not entirely sure, but there is a reaction on Zoom. So there's lots of things that we can play around with. Okay, so we're going to do a few more here in this form, and then we'll get into kind of some more complicated ones. So on the left, we've got negative 125/36 plus 25/6, then minus 5 plus 6 minus plus. It's going to keep alternating. So this is an alternating geometric series. So the steps are the same as the one we just did. We have to identify what A1 is. We have to identify R, and then we basically put it into the formula. So A1 is the first term, so that's going to be negative 125/36. Then R is A2 divided by A1. And you know what? These are two fractions, 25/6 divided by 125/36. Because we have a constant ratio, this is going to be the same as if we took A4 divided by A3. And A3 and A4 are both whole numbers. So it actually would be a lot easier if we use the whole numbers to find our ratio versus the two fractions. We'll get the same answer, essentially, or we should, but it just may be, easier to do. So A4 is 6, and then A3 is a negative 5. So you have to include that negative there. And so there we go, negative 6/5. I'm not going to bother going through the 25/6 divided by negative 125/36, but it will get you the same thing. So That's the nice thing about geometric series. And actually you can do this with the arithmetic as well, but you don't have to always pick the first two terms to find your R. You can pick the ones that look the easiest. And so Toby, I see that's what you did, you know, as long as they're one after another, pick the ones that are easy. So our sum here is going to be A1. So that's negative 125 over 36. And now, because we've already got a fraction there, it might be easier to use this intermediate step where I had the A1 times 1 over 1 minus R, just because we're going to be multiplying by another fraction. Or, you know, you may want to just leave it as the A1 over 1 minus R. I'm going to do it this way though, so I don't have a fraction on top of a fraction, or at least it might look a little nicer. So we've got multiplied by 1 times 1 minus a negative 6 over 5. Now for something like this, go ahead and use your calculator. Don't worry that, you know, you have to show all work here. What's important is that I want to see the setup. You know, what number did you plug in? And then you can give me the final answer. And if you do not have a calculator that can do fractions, most calculators do, or at least scientific ones. So I've got, oh, you can't see it because I've got the background on, but I've got the TI-30X and it does do fractions, but it's kind of hard to enter in. So I actually prefer to use Desmos for my fractions. So I'm going to just do the scientific calculator. And then it just has a fraction button. Whoops. So I can just set up all of my fractions right here. And then it will give it to me in the decimal form, but I can hit the fraction button. And then that way I don't have to go through and do all of the math here to try to figure this out. As long as you show me what, you know, your setup was, then you can give me that this final answer is negative 125 over 77. So that is what the sum comes out to. So now let's have both of you guys do the one on the right here. So A1 is very clear, the first number, 9. What is R? So we have 1/9 minus 1/3 plus 1 minus 3. What is R? -3. Okay, that's great. So, and this is another one that I would take the -3 over 1. I would do the A4 over A3 in order to figure that. So we've got R is -3. So go ahead and find me the sum. Okay, we get a 3.111. That is not what I got when I put in my calculator. Maybe I put it in my calculator wrong. I got something different. So let's see. So we've got 1/9 divided by 1 minus a -3. So that's 1/9. And then that's going to be 1 plus 3, which is 4. Yeah, this should come out to 1/36. Yeah. So when I put in my calculator, you have to make sure that you've got your parentheses all in the right spots, or you have like your divisions all in the right spot, because if you don't, then your numbers could come out to be wrong. So these were the two answers we got for the sums. Now, what I want to point out to you is, remember that I said over here that we want R to be less than 1. And I said, you're never going to get ones where R is going to be greater than 1. What did we have in these two situations? Both of these values for R are greater than 1 when you take the absolute value. So we have this rule that the absolute value R is less than 1. These both actually don't follow that rule. And so I said, you're not going to see these, and you're not going to see something like this, like on a quiz or anything like that. And of course, not on the application assignment. I put these specifically in this session here just to kind of get you thinking. So we got answers with our formula, but these are not actually valid answers because the formula only works when the absolute value of R is less than 1. So you can use the formula and get answers, but there isn't actually a sum. These numbers aren't actually the sum. They're kind of meaningless because our values for R are actually, the absolute value is greater than 1. So for both of these, if you were to encounter this, and it doesn't happen very often, but for both of these, it's actually greater than a 1. So what you would say is the sum is undefined. Because technically these go on forever, and the numbers keep getting larger and larger and larger, and so the formula is not valid. So I threw these in here just to kind of, make you think about that, because what happens is, you just go through, you do your formula, and you don't even think about, wait a minute, R has to be, the absolute value of R has to be less than 1. And the formula gives you numbers, but it doesn't, the numbers don't really mean anything. So like, let's take this sum being 1/36. If we just took our first 4 terms here, 1/9 minus 1/3 plus 1 minus 3. Oops, I forgot a minus sign on my calculator. You get -2.22. And your R is a large number. So you're going to keep getting further and further away from this sum. And you can test it out on your own if you want. But you're not going to get remotely close to 1/36. That's what the formula gives us, but it doesn't mean anything. So I just wanted to put these two in here to kind of throw you off and just to make you think, but this is not going to be something that's on a quiz or anything like that. Just something to make you think about the assumptions when you have formulas. That every formula has an assumption, and if those assumptions aren't true, your result doesn't mean anything. So are there any questions about that? Okay. So I want to do this one just because this is in the alternate form of the geometric series, where we don't start at 0, but we start at 1. But the formula still works as long as the exponent is k minus 1. If you were starting at 1 and your exponent was k, you can't use the formula because it's not in the right form. So just as kind of a note here, if you had k equals 1 to infinity, and then it was like 1.3 1 over 10 to the k, that doesn't work because you're missing a term. If you have just the k, your first term would be 1.3 times 1 over 10. And so you're actually missing that first term, which would be just 1.3. So just as a side note, if you have your index starting at 1, the exponent needs to be k minus 1 in order for them to be equivalent. Otherwise, you'd have to add in an extra term. So this would be the same as if I had 1.3 plus the sum from k equals 1 to infinity of 1.3 is 1 over 10 to the k. So if the exponents, you've got the k equals 1 and then a k, you have to really add in an extra value in order for it to use the formula. So just a side note, and I'm bringing this up because this is something that I see on that last problem on the application assignment. And so I'm specifically bringing this up because this is something that I've seen where people have treated them equivalent and they're not, and then they actually get the wrong answer. So just an important note there. But as we've got the formula in white, that is equivalent, so we can use the formula. So our A1 is equal to 1.3 and R is equal to 1 over 10. And that's a number less than 1, so we're good. You know, we can find the sum. It will mean something. And so we can use this formula. So we have 1.3 over 1 minus 1 over 10. Now, I know, one thing that I say all the time, if you've taken classes with me, don't mix decimals and fractions. Here we've got a problem that mixes decimals and fractions. It's okay, intermediate steps here, to use 1.3 and then 1 minus 1 over 10. It's okay because it's not our final answer. But in our final answer, you want to stick with either decimals or fractions. But generally, we'll stick with fractions because those tend to be more exact and we don't have to round. So just a side note there. So we just have to convert this 1.3 divided by 9/10. And then it is a repeating decimal, so I'm going to convert it to a fraction. And this gives you 13 over 9. So it's actually easier to write it in fraction form rather than the decimal form. But you wouldn't want to leave your final answer with both a decimal and a fraction. So it's just not good form. It works, but mathematically it's just not quite simplified all the way. But if you do it in the intermediate steps, that's okay. Are there any questions on this example? Okay, so I'm going to finish up with 2 word problems, and yes, these are looking very lengthy. Don't worry. Okay, so a state government gives property owners a tax rebate with the anticipation that each property owner will spend approximately some percent of the rebate, which in turn then the recipient of that amount will spend some percent of what he or she receives, and so on. So if I got $100 and say I spend 10% of that at a store, the store owner gets that money and then they're going to use that money and spend 10% of it. So there's just some percent that you're assuming that if you get income, you spend some percent of it, and then it kind of gets passed through the economy. So economists refer to this exchange of money and its circulation within the economy as the multiplier effect. The multiplier effect operates on the idea that the expenditures of one individual become the income of another individual. So for a tax rebate of $400 and the percent being 75%, find the total amount of spending that results, assuming that this effect continues without end. So what we've got here is, like, let's say the government is just paying you $400. So person 1 just got $400. The way this works is that you then spend, they're assuming 75% of it. So you spent 75% of that $400. And that becomes income for person 2. Then person 2 has just received that much money, and then they spend 75% of that. So they have 75% of what they just received. And then that goes to person 3, and this is essentially what's happening. And so you can see that this is geometric because each person or each, that this money is getting passed on to, you're getting another 75% on it. So that's your R. And your A1 is that $400. And so the total amount of spending is the sum of these values. So this is a geometric series, and they're saying it goes without end, so it goes on infinitely. And so finding this formula, finding this total gives you an estimate of how much economic spending this money is going to generate. And this is actually something that economists do to help decide when they say that if we give everybody $1,000 rebate or something like that, it's going to generate this much spending in the economy. This is literally the kind of formula that they're doing. So we've got A1 being 400 and R is 75% or 0.75. And so this is a geometric series, and they didn't give us the formula, so I should actually put it in summation notation because they haven't actually given us the sequence. So good practice is to put it in summation notation first. So I start I at 0 to infinity of 400 times 0.75 to the I. So it's good to put it in that form first since they didn't actually give you the sequence. And then you can use the formula, 400 over 1 minus 0.75. So it's 400 over 0.25, which is 1/4. So that's going to be $1,600. So for this tax rebate, the total spending that will result, if you give one person $400, this is going to generate $1,600 of spending in the economy. So then think about, okay, let's say you give the, 100 people this, it's going to generate even more. You just multiply this by 100. Or, the population of the US, if you give every single person in the United States a $400 rebate, and this is what you're assuming is happening, you can take this result, 1,600, multiply it by the total population of the US, or the total amount of people that would be getting that. And then that would be the generated economic spending that you would assume that this occurs. So I really like this example because it shows you kind of what goes on in the government and how they come up with these numbers. The 75% though, that's an arbitrary number. How do you know we're going to spend 75%? You have to kind of make assumptions and kind of do some research to figure out what that actual number is before you can do this calculation. But I love math, and I also love economics. And the one thing that always fascinates me is that you've got the budgeting office that always comes up with these estimates, and it's like, well, how do they come up with these estimates? And this is, one way they do it. So they're actually, using a lot of math that you wouldn't even think about. There are questions on this example. Okay, so this is my last example, and I like this one because this actually reminds me of something that I learned in I think it was actually my geometry class, so I don't know why it was geometry. Maybe it wasn't geometry. It was in high school. My math teacher in high school talked about this. So can the Greek hero Achilles, running at 20 feet per second, ever catch a tortoise starting 20 feet ahead of Achilles and running at 10 feet per second? The Greek mathematician Zeno said no. When Achilles runs 20 feet, the tortoise will be 10 feet ahead. So I'm actually going to kind of draw a picture here, because this is one where it's like, I need a picture. So Achilles is here. And then we've got this little tortoise right there. And so Achilles is going 20 feet per second. And this magic tortoise is going 10 feet per second. Obviously, when this was, done in the Greeks, they weren't doing feet per second because feet didn't exist then. They had some other measurement, but, this is what we're working at. So when Achilles runs 20 feet, the tortoise will still be 10 feet ahead. Then when Achilles runs 10 feet, the tortoise will be 5 feet ahead. And Achilles will keep cutting that distance in half, but will never catch the tortoise. So following Zeno's reasoning, find the total distance Achilles will run and the total time it will take. So let's kind of think through this. There's a 10-foot gap right now. And let's just make a table. So let's have Achilles, the tortoise, and then let's just put seconds over here. So we'll use the time. So at time 0, Achilles has gone is 0, but the tortoise is 10 feet ahead. Let's say they've gone 1 second. So since Achilles runs 20 feet per second, he has now gone 20 feet. The tortoise runs 10 feet per second. He's already 10 feet ahead. So he's going another 10 feet. 10 feet, let's see. So this would get them to match. So you would think, okay, he's going to run ahead. But the way that Zeno is thinking about this is he's thinking about this in like you're cutting it in half and half and half. So let's say we go, oops, not. So logically, you're thinking, okay, 20 feet per second. So now Achilles has gone 40 feet, and the tortoise has moved another 10 feet. So he should be at 30. So the way, he's, you look at this and you think, okay, here's how it works. Achilles should catch up to the tortoise. And then he should exceed the tortoise. But Zeno has this thing called Xenos Paradox, where he kept thinking, he was thinking, well, wow, whatever, let's say in order to reach the 10 feet that the tortoise goes, I have to first go half that amount of time. And then I have to go half again. And so he kept thinking about things in terms of you have to go half the distance, and then half the distance, and then half the distance. So the way that Zeno is thinking about this, and this is really crazy, and that's actually kind of why I like this problem, because it's called a paradox. It's called Zeno's Paradox because it doesn't seem to make sense, but it also makes sense. So Zeno is saying, okay, let's make a new table. So at time 0, is at 0, let's say at 1 second, it's gone 20 feet. Then at second 2, he's gone 10 feet. And he keeps cutting the distance in half. This is the way that he keeps thinking about it. This would be 2.5. So he just keeps thinking you got to go half by half by half by half. And if you think about it, you're like, okay, if I have to go 20 feet, I first have to get 10 feet. In order to reach 20, I have to at least get to the halfway point. Then I have to get to the halfway point, and so on. So this is what he's thinking is like, how much distance do you move kind of in each second? So I actually pulled this from the textbook and it had a table. We're gonna bring up the textbook here. Toby says you're gonna dream about this. Yeah, I remember like when I was in school, my high school teacher would be like, okay, you're trying to walk to the wall, go half the distance. Okay, go half the distance again, go half the distance. And it's like you keep getting closer, but like technically you'll never get there technically. So that's what makes it a paradox. But you know, obviously we know that Achilles would catch up to the tortoise, but Xenos says if you think about it this way, he won't. So if we, this is, he's thinking about it this way. So I should have done the time differently, the way that it was worded. So in 1 second, you go 20 feet, which means in half a second, you go 10 feet, which means, okay, if you take half of that, you've only gone 5 feet and so on. So he comes up with this table, and then you can do the infinite geometric series on here to figure out, okay, what is the actual distance that he can run? And then what is that, the total time basically. So let me change these. I think the wording on this problem is kind of confusing. There we go. So this is really what Zeno was saying, is that you can go half the distance in half the time, and then you can go half the distance in half the time. So we can do 2 infinite geometric series here. We can do one with time to find the total time it will take according to Zeno. And then we can do one with distance to find the total distance you will run if you did this forever. So let's do the distance one. So your R would be basically 1/2 because we're taking 1/2 each thing. And our A1 is obviously going to be 20. So for our distance, the total distance is going to be 20 over 1 minus 1/2, which is going to be 20 over 1/2, which is going to be 40. So if Achilles theoretically always went half the distance, according to Zeno, he's only going to get 40 feet and then he'll stop. He'll never get further than 40 feet because he's always trying to get half and half and half. And the distance that you go for half is smaller each time. And then we should get a time of 2 because that's, you know, what I did with this table here. But if we do time, so again, we're taking half the time, but now we're starting at 1. And so you get 1 minus 1/2, which actually that just comes out to 1/2 in the denominator. 1 divided by that, you get 2. So according to Zeno's reasoning, in 2 seconds, he'll go 40 feet. And that matches what we, you did. If what we did on, what's actually happening every second you move 20 feet. But Zeno's saying, no, he's not going to get any further than that. He's never actually going to catch up to the tortoise because he's going halfway every time. It's this really weird, convoluted thinking. It's called Xenos Paradox. He also has, I think, 3 paradoxes. He has another one with an arrow, that an arrow is always at rest when it's in flight, because at every, like if you took a snapshot of an arrow at every second of time, it's not moving. So while the arrow is moving, it's also not moving at the same time. Really, really interesting guy. But I picked this one because in one of my math classes in high school, we talked about this paradox, and I just thought it was kind of interesting, the different way that you can think about it. Obviously, we know the right answer. Yes, he's going to catch up. But, if you look at it this different way, it seems like he never will. So, any questions on that? I lost the chat. Where did my chat go? Yeah, any questions on this example? This one was less about using the formula and more just to kind of some of the crazy things about math that mathematicians think of. So definitely worth looking into. I'm sure there's a YouTube video on Xenos Paradox. I'm sure there's some really great videos. Even better. Okay. So I just put it into Google. Numberphile is one of my favorite math channels, and they have a Xenos Paradox. And here's the one about the arrow being at rest. This is another guy. This PBS Spacetime, he does some really good videos. So, you know, if you're curious to learn more about it, you can watch, you know, put it into YouTube, and here's one about the tortoise and the whole thing. But I just wanted to do this last one just to kind of just as something interesting other than what we've been doing this whole time. So that's all that I've got for you guys tonight. Do you have any questions on anything like the application assignment or anything else that I can maybe help you out with? Oh, okay. So I'm glad that I already covered it. So great. All right. So I will let you guys go, and you know, tomorrow I'll send this out and we'll see how this Zoom ended up. I'm not sure what the recording is going to look like, so it'll be interesting because I haven't used this before. I figured I'll use you guys as a test before I do it in my other classes. So thank you so much for attending. I hope you guys have a great night, and I'll see you at the next live. So bye. Thank you.